definition of this. So in this case, we have various samples. Samples of an input signal are sampled and they are held at the previous value. That means this system should have some storage element also. So as a storage element, we make use of a capacitor. So we make use of two elements primarily, a switching device, which is a MOSFET here. So switching element that is used here is a MOSFET. So we generally make use of E-MOSFET or enhancement MOSFET since it is faster in comparison to P MOSFET. And in terms of size also, we have seen that an NMOS is smaller in size in comparison to a PMOS. So switching element MOSFET creates the samples. So this is used to create or generate the samples. I told you the meaning of sampling. Sampling is the process of breaking the information, or it is the process of dividing the information into finite samples, very small samples. And this is done for this purpose. We select a frequency called as sampling frequency. And this sampling frequency is governed by the Nyquist criterion. The maximum sampling frequency has to be twice of the supply frequency maximum. Right. So one element which is used here is a MOSFET. Another element which is used as a storage element is a buffer. Storage element that we are using is a capacitor along with a buffer. So this capacitor voltage is applied to a buffer and the buffer supplies the output. So this buffer amplifier finally generates the output which is derived from the circuit. So let's have an eye on the circuit, how the circuit looks like. So we have an op-amp. First of all, we have an EMOS on this side. So this is the MOSFET that is used on the input side, and to the drain of the MOSFET we are connecting the signal source which has to be sampled. So this is the drain terminal here, and this is the signal source that is being attached for sampling purpose. Let us name it as V in. This is the input voltage. This is further connected to a here to the gate of this MOSFET. We are connecting a sampling voltage. So this is the sampling pulse that is applied here. So depending upon the sampling pulse, which is also called, we can designate it by Vs. This is connected to the gate of the MOSFET. That is designated by G, and this is the source terminal which is generating the output. So here we have a resistance in between the MOSFET and the buffer. Now we are using a buffer here further. So after this, a buffer amplifier is used. You know the gain of a buffer amplifier is 1. So that means it does not load the source. It is connected in this manner with the inverting terminal connected to the ground. This is terminal number 3. This is terminal number 2. And this is the output terminal 6, where from we get the voltage. Across this we have a load resistance RL, across which we get the output voltage. So output is obtained here. So if you look at the entire circuit, this is the switching circuit here. This is the switching element, as I have designated earlier. And then for the purpose of storage, here before the resistance we are using a capacitor. So I'm adding one more element here which is very crucial. This is required for the holding operation. So capacitor C, which stores the voltage, it is getting charged up to a voltage called Vc, and this voltage is finally translated into the output voltage. So we can say that output voltage is approximately equal to the voltage across the capacitor. Now we will see how this circuit functions. So this side of the amplifier, if we look at on this side, this is the buffer amplifier, right? Then this is the sampling device. So this is the sampling section. Here the sampling takes place, and at this place the holding takes place. Holding means that the whatever value is produced at the output of the MOSFET, it is held and it is stored till the time next sampling is done. So the sampling instant or the sampling speed is decided by the sampling voltage source. This is the sampling voltage source Vs here. Now let us see, we will precisely write down the operation of this device in finite steps. So this works in the following manner. First of all, the signal V in is applied, as I told you. Signal V in is which has to be sampled is applied to the drain, as we have done here in the circuit. And then the sample and hold voltage Vs is applied to the gate. So Vs is called as the sample and hold voltage. This is sample and hold voltage. We will see in the waveform what is sampling instant and what is the holding instant. Now what happens during the positive half cycle? Again, we'll break the operation into positive and negative half cycles. So during the positive half cycle of the supply waveform, or rather here we should talk in terms of the control voltage. So during the positive half cycle of Vs we'll talk about, because this is the control voltage. E MOSFET will switch on. E MOSFET conducts or it switches on. It is on or it conducts. Once it conducts, it acts as a closed switch. You know, when the MOSFET conducts, it acts as a closed switch. Because of this, the voltage which we are applying, it applies the input voltage to charge the capacitor. So in this case, the input voltage, now what happens? The input voltage which is applied, input voltage V in, passes through the circuit. It charges the circuit. It charges the capacitor, right, up to a voltage Vc, right? So the input voltage appears across the capacitor and same voltage is translated to the output. So whatever be the input voltage at this time, same voltage appears at the output, because this voltage passes through a buffer amplifier, and you know buffer amplifier does not change the level of the voltage. Therefore, whatever voltage is visible or it is applicable here at this terminal, which is Vc at this point of time, the same voltage will appear at the output. So I mentioned here output voltage equal to capacitor voltage. This is happening when we talk about the positive half cycle of the control and the sample and hold voltage. Now, during the negative half cycle, opposite will happen. Now we will discuss the negative cycle. So during negative half cycle, reverse of this thing will happen. E MOSFET will now be switched off. So E MOSFET is off at this time, and now the voltage across capacitor will appear at the output. Across the capacitor will appear across the output. Why? Because this voltage of the capacitor will remain more or less constant, because the buffer amplifier has got very high input impedance. If you know this thing, that input impedance of the buffer amplifier is very high, because of which the capacitor does not discharge fast. It takes a longer interval of time to discharge. And if you remember in the previous circuit in the peak detector, I told you that the capacitor does not discharge for more than 10 T cycles. So capacitor remains charged up to 10 cycles of the input supply, right? So the time intervals which we look at, if I draw the waveform of this particular circuit, you can see, we'll discuss in terms of the waveforms now. Now this is the supply waveform. First of all, we'll draw the input supply waveform. This is the sampling waveform, and finally we'll get the output. So if this is the supply here, this is the input voltage, and this is the peak value of the input voltage. Now corresponding to this, we will draw other waveforms. I told you yesterday that the input waveform is also called as the mother waveform because it serves as a reference waveform for all other waveforms, right? So if this is the supply, this is the sample and hold voltage. You may draw it at a better scale. So this is the sample and hold voltage, and let us see how the output looks like. We can draw the projection of these waveforms. This waveform is Vs, sample and hold, which is a square waveform. And finally we have output waveform, which is nothing but it is the voltage across the capacitor. So we can imagine that we are drawing the projection in the reverse sense also. So in that manner also you can imagine this waveform. So up to this point in which the capacitor is charging, it will come up to this point, it will come here. I'll go back. So the final waveform or the output waveform will be like this. Up to this instant, input and output will be the same. Then the capacitor will come into picture. Then after that, this waveform is coming down. And at this instant, again, the capacitor will be there. Then again, the capacitor will charge. And like this. So it is not syncing exactly, but we can draw on a better scale and find out. This is the instant when the capacitor voltage, this is the voltage across the capacitor which holds this straight line is because of the voltage of the capacitor. Wherever you have straight lines, they indicate the charge of the capacitor, and wherever you get the waveform like this, like it is similar to the input waveform, wherever the output resembles the input waveform, that is the time which is called as sampling time. So this time during which the MOSFET is on, this is designated as TS, where TS is called as the sampling time or the sampling period. So sampling period is that period during which the MOSFET is on and the voltage across the output is the same as that of the input. So during the sampling interval, if you look at this, the input follows the output. The output and input are same. Then the second instant, which is called as holding instant or TH, this is called as hold period, right? Or holding period. So holding period is that period during which the output is due to the voltage of the capacitor. During holding period, MOSFET is switched off. So MOSFET is off during this time. This is the off period of the MOSFET. During sampling period, MOSFET is on and the output is available across the output. So during sampling period, we can say output is equal to input waveform, and during holding period, output is equal to the voltage across the capacitor. So whatever voltage is developed across the capacitor, that is available across the output, right? So we can define these two time intervals, TH and TS. So TS is the sampling interval, right? So TS is the time period of the sample and hold control voltage. It is the time of the sample and hold control voltage. Hold control voltage. All right. Similarly, we have another interval which is called as TH. So time period TH is during which the voltage across the capacitor is constant. So during this time, voltage across capacitor is constant. I told you the reason for this, why the voltage across the capacitor is constant. So voltage across the capacitor is constant during this interval because when the capacitor tends to discharge, it has to discharge through the buffer, but since the buffer input impedance is very high, therefore the capacitor cannot discharge easily. Therefore, it maintains the voltage at its threshold level. So output voltage is nearly equal to the voltage across the capacitor. And similarly, the condition which is necessary for proper approximation of this. So for proper approximation or for proper performance of the circuit, so for proper approximation, what is required is that the sampling frequency should be much greater than the input frequency. So, but as we have already decided, we know by the principle of sampling that the sampling frequency is governed by the Nyquist criterion, right? And now, as far as the applications of this circuit are concerned, we have the following application. You can note down the application. So the area where this is used is generally it is used in digital interfacing, or it can be a part of the communication system. In digital interfacing it is used, and in communication systems, digital interfacing and communication, for analog to digital conversion. So for A to D conversion, analog to digital conversion, it may be utilized. And as I told you, it can be used in pulse modulation systems. So wherever we use digitization or modulation in pulses, pulse modulation system can be PCM, PPM, etc. Right? So pulse modulation systems also we can incorporate a sample and hold circuit. Is there any difficulty in understanding this circuit? Any difficulty in understanding this circuit? So circuit is quite simple. If we look back into the circuit, let us have a glimpse of the circuit again. It comprises of a MOSFET as a switching element, to which the gate of which we are applying the sampling voltage. Sample and hold voltage is applied to the gate, and the voltage which has to be sampled is applied to the drain. The output generated at the source terminal passes through a buffer amplifier, and before it goes to the buffer amplifier, it charges a capacitor. Role of the capacitor is to maintain the output voltage at the threshold value. That means in the absence of the MOSFET, when E MOSFET is off, even at that point of time, the output voltage is constant. So this was applicable in case of flip-flops also. We saw that the flip-flops, we discussed a node capacitance as the output capacitance, where the voltage was either 1 or the voltage was either 0. That means the output was either high or it was low, and that was deciding the memory bit which was stored in the that particular flip-flop. Okay.